Okay, we're in section 20 of the notes. This is going to be the assignment on radicals. So the problem with this over here is that certainly we're going to go through some rules and some conventions that we have. And the big problem there is that it's going to be, what I do say a lot of detail. I do want to emphasize, though, the detail may be incredibly dry for students. So we're going to eventually get to problems, all right? But before we get to problems, we got to go through these details. So this lecture is going to be a little bit longer than most other lectures, but it's still a relatively short lecture. We're going to try to hammer this across, though, in examples. So I'm not asking you to memorize everything that's been stated, but when we get to the work, if we get to the problems, you should start to appreciate what was said during lecture in more detail. And you might have to go back and read the notes again or look at the videos again, whatever works for you. All right, so let's go to the whiteboard now. All right, let me do that, new share. And I'm going to talk to the whiteboard. And we're talking to the notes, actually. All right, let's take a look. All right. Okay. I'm going to highlight her out. And we're simplifying radical expressions. Whoops. Okay, let's read. So the nth root of A and the nth root of B. Now, after positive numbers. All right, what do we got over here? We have the nth root of AB is the same thing as the nth root of A times the nth root of B. All right, well, that's nice to know. We could also say this, the nth root of A times the nth root of B equals the nth root of the product AB. All right, let's take a look at an example. An example they give me is this one over here. So what do you see? You see the square root of 75. So the square root of 75 can be written as the square root of 25 times the square root of 3. Right? The reason for that 25 times 3 is 75. And the square root of 5 now, I'm sorry, the square root of 25 is 5. So we have 5 root 3. So, if I were to write this down, this might seem strange to you. The square root of 75 is identical to 5 times the root of 3. Now, this is going to be our goal, by the way. We're going to take a look at roots and we're going to rewrite them. Now, someone says, why would you rewrite it? I like the root of 75 better than I like the root 5 times the root of 3. And I'll be honest with you, I kind of agree with you. I think this here looks simpler than this thing over here. But our goal is to go in this direction over here. Now, so you might say it's complicating it. It is going to make the problems that we present to you easier if you can do this. But let's keep reading. All right. So the next thing it says, you may wonder what the root of 3 is. Right. I'm going to say that there is no numerical representation for the root of 3, other than we could just simply say it's the square root of 3. All right. You could try it on your calculator, though. And a calculator is going to give an approximate value to it, but it's not going to give the exact value to it. The root of 3 is just the root of 3. On most modern calculators, though, when you type in the square root of 3, the calculator will just spit back root of 3. Right? So what I want to claim, if you want to get a calculator to actually do an approximate, what you're going to do is force it to do so. So let's take a look at an example of forcing a calculator to actually give you an approximate value. All right, let's look at this example over here. And what I'm going to claim, I'll move this over a little tiny bit. What I'm going to claim is if you wrote down the square root of 75 on a modern calculator, it would write down 5 root 3s. Now that doesn't help most students. They still don't know what it is. Now I hope you realize the root of 75. Oops. Is between two numbers. Now I'm going to look at perfect squares. What's it between? And what's the perfect square smaller than 75? And I'm talking about perfect squares, by the way. What are the perfect squares? Like 4, that's 2 squared. 9, that's 3 squared. 25, whoops, I forgot 16. Wasn't thinking. 25. Let's see, 2 squared, 3 squared, 4 squared, 5 squared, 6 squared is 36, 7 squared is 49. Let's see, 8 squared is 64, 9 squared is 81. So I'm going to say 75 is definitely between those two numbers there, which is 64 and 81. So I'm going to say, in my little mind here, that this number, whatever it is, square root of 75, has got to be between 8 and 9. All right, let's talk about forcing a calculator to do the computation. Again, if you go to calculator and you put root 75 down, it's going to spit back. And I say a calculator, a modern calculator, 5 root 3. If you want to force it though, what you're going to need to do is put this down, 75.0. If you do this, the calculator is going to say you want an approximate. Now someone says, if I want an approximate, how good could it get? Well, as good as you like. Modern calculators can really go out to a high level of precision. Now I'm doing kind of ridiculous over here, but I kind of said, my calculator gave me this thing over here. All right. Now, certainly we don't need that level of precision. For the most part, if you get like, 1 or 2 places, that's pretty good. All right. Now, remember what I said? I said it was between 8 and 9. And certainly my calculator does a much better job than saying it's between 8 and 9. It comes with a pretty good approximation. All right. So let me just talk about another root, root 7. Now, again, I believe you should have some idea that this is between 2 perfect squares. And we'll talk about that in a second. And what's the perfect square above 7? Well, it'll be 9. What's a perfect square below 7? It would be 4. So I'm going to say the root of 7 is between 2 and 3. All right, now if I use a calculator and I want to get the square root of 7, again, I want to plot on a calculator. If you type in root 7, a modern calculator would just simply put back root 7. What do you have to do? 7.0. If you do this, the calculator is going to give you an approximate answer to that. To a high level of precision, by the way. Typically, we don't want to go too far with it. So I'm going to say typically we would like to go to the nearest hundredth. Again, a calculator, the square root of 7 is approximately 2.65. All right. All right, let's talk about initial simplifications. Generally speaking, we do not want you to use a calculator to do these problems over here. So I'm going to say a radical expression. What is that? It's something that contains a root symbol. What's your root symbol look like? It's got something like this in it somewhere, right? Nth root of something. We're going to say it's in simplest form when the radicand. I want to point out what the radicand is here. The radicand in the problem is going to be what's inside here. That's the radicand. Goes on to say in parentheses there, the thing inside the root symbol. Here's the problem. A lot of students read this and have no idea it's been stated. It says contains no factors that is a perfect power. We're talking about this power over here. All right, so let's talk through it. So I'm going to put the 27 down. Whoops. And the index, that's the number that's here. Since there's no number there. Well, index over here, there's no number there, it's 2. So the index is 2 here. So what am I looking for? Perfect squares. All right, what are the perfect squares? Let's write them down for you. 2 squared is 4. 3 squared is 9. Then you get 16. Then you get 25. Then you get 36. And you should realize this list goes on for a very long time. It goes on forever. So what I'm going to do, I'm going to say that, does that 27 contain? Now someone says, what does contain mean? Is it a factor of? Well, what do I notice immediately? I notice that 9 is a factor of 27. So I'm going to write that down. I hope you can agree that 9 times 3 is 27, and 9 is in fact a perfect square. So what do we do now? We split it. It can't contain that. So what I'm going to do is I'll write it down this way now. Then the problem comes is, do you know what the square root of 9 is? And you do, it's 3, so it's 3 root 3. So my claim over here, the square root of 27, I do know it's between two numbers. I know it's between 5 and 6. And why is that? The square root of, I'm sorry, the square of 5 is 25, and the square root of 6 is 36, so certainly 27 between those two numbers. But they're not asking me what it's between, they're asking me to simplify it. So what we want you to do is, instead of writing down the square root of 27, which you should know is between 5 and 6, what we want you to write down is this thing over here. And why is that? Our radicands cannot contain a perfect square for square roots, and it did. All right, let's go to the next page. Let's look at the next one. And again, this is more difficult. And the reason being is it's the cube root of 48. I'll write this on the side for you. And this is going to be the cube root of 48. So what am I looking for now? Perfect cubes. What are the perfect cubes? Well, 2 cubed. 2 times 2 times 2 is 8. 3 cubed. 3 times 3 times 3 is 27. 4 cubed. 4 times 4 times 4 is 64. No, you don't need to write them down. What you need to recognize is 48 contains one of those numbers. What I mean, it's a factor of that. So let's write this down. So it's going to be the cube root of 8. Well, 8 times what? That's 6, right? All right, let's keep going. I'll write this a little differently as the cube root of 8, cube root of 6. What's cube root of 8? It's 2. Cube root of 6. So the cube root of 48 should be written as 2 cube root of 6. All right, our goal is to do that. All right, so if we have a perfect cube and a cube root, we need to get rid of it. All right, let's look over here, make sure we got that written over here. We do. And next thing up, we have these letters over here, and they're a little more difficult. All right, so let's put this one down. And I want to emphasize what we're looking at over here. We just did this one. Now we're going to look at this one over here. All right, and let's go through it. All right, so it's the 5th root of x to the 6. It's the 5th root of x to the 6th. So what am I looking for? Perfect fifths. All right. Well, these are going to be numerical in nature. I'm sorry, these are going to be letters in nature, right? Variables. So x5, x10, x15, yada, yada, yada. Does x5 contain one of those factors? And it does. What does it contain? This one over here. Let's write that down. The 5th root, x5 times x equals the 5th root of x5 times root x. Let's see, what's the 5th root of x5? It's just x. And why is that? X to the 5th power is x5. Whoops, forgot to put the 5 there. 5th root of x. So our goal here is, if we see this, and it's going to take practice to get there, by the way, I'm not saying get this initially, we're going to write this down instead. All right, let's keep going back to the notes. And I want to point out what that's written down for you. And we did this one here. And we did this one here. All right. Let's get the next thing up. And again, if you can understand what we just did over there, this is going to bode well for future problems. All right. Let's look at the next thing. And what we're going to be doing now is adding and subtracting radicals. All right. So, you know, I realize that sometimes you make these things really complicated. We're not trying to. We're just trying to point out some information over here about the distributive property. So I'm going to say over here, if you look at this one over here, it's really the same thing as saying the root 7 times 5 plus 3. All right, why is that? You get 5 root 7 plus 3 root 7. All right, what's 5 plus 3? 8. So what are we doing in appearance over here? I want to claim what we're doing in appearance over here. We see the two terms. The two terms have identical radical part. The only thing we're doing is we're adding their coefficients. And what's 5 plus 3? 8. 8 what? 8 root 7s. All right, let's look at another example. And I'm saying it may look bad to you. I mean, you're looking at this and saying, what do I want to do with this one over here? Well, let me just pull it to the side. And we'll go through it one step at a time. And then we'll go back and look at the key. All right, what's my goal over here? Is to combine these two terms. There's two terms in a problem. My first issue, though, is the root of 8. It's got trouble. And what's the trouble going to be? They want me to simplify it. And let me write this on the side for you. So the root of 8, it contains a perfect square factor, which is 4 times 2. The square root of 4 is 2. So it's 2 root 2. Let me write that down. So I get 3 times, well, the square root of 8 is 2 root 2s. Let me write that down. All right, let's keep going. What do I notice now? Well, the first term, I need to simplify it. And the way I'm going to do that is combine those two things together. And what am I doing? Make an association. And what's 3 times 2 is 6. What do I notice? I have two terms that have identical radical parts. What am I going to do? Add their coefficients together. Well, what's 6 minus 5? It's 1. 1 what? 1 root 2. We normally just write down root 2, though. It's 1 root 2. Let's go back. Make sure you know that in the key, I say the key to what we're doing over here. And we see that right over here. All right. Multiplying radicals. All right, we're going to multiply radicals. All right. The nth root of A times the nth root of B is the nth root of AB. Well, we introduced in the beginning. I'm sure you remember that. Now, what they have to do, they have to have the same index. If they don't, we have troubles. We can work around that, but I'm not going to say we'll get there in this semester. All right, let's take a look at this over here. And I'm going to write that down on the side. That's root 24 times root 27. All right, what I'm going to claim over here, what happens to a lot of students is they do exactly what they've been told, which is to multiply the 24 times the 27. I'm not going to say there's anything wrong with that. What I'm going to claim, though, is those numbers look too big for me. All right, so what I want to do is I want to look at these numbers separately. I want to look at the root of 24. And remember, we give you problems that you're capable of doing. We're not trying to give you things you can't do. We're trying to give you things you can do. Now, does 24 contain a perfect square factor? Well, I'm going to write this down. What's a perfect square factor? 4. 4 times what? 4 times 6. What do you get over there? 2 root 6. All right, let's look at root 27. Then my question over here, does 27 contain a perfect square factor? And it does. It's 9. What's greater than 9? 3. So I'm going to claim that also this root 24 times the root of 27 is identical to 2 root 6 times 3 root 3. I'm going to do some commutations and associations. I'm going to take the 2 and 3, move them around and associate them. And I can take the root 6 times root 3, and again, move them around and associate them. Again, in time, you're going to get faster. What's 2 times 3? 6. What's 6 times 3? 18. All right, we're not done yet. And I know it looks horrible. I realize that. Does 18 contain a perfect square factor? And it does. It contains a 9. 9 times what? 9 times 2. Yes, a lot of work, right? 6 times 3 times the root of 2. What does it give me? 18 root 2. No matter how I do this problem, provided I do not make a mistake, it's always going to be 18 root 2. All right, so what I'm going to claim over here is that I don't mind you doing this. Somebody says, no, I don't want to do what you just did. I want to do this instead. If you're going to do this instead, what you're going to do is 24 times 27, and you need to multiply it together. Let's go through that. 7 times 4 is 28. 7 times 2 is 14, plus 2 is 16. 2 times 4 is 8, and 2 times 2 is 2. What do you get there? 8. Well, let's see, 6, that's 14, right? 44. I'm sorry, 448. All right, make sure I did that right. 814, yeah, 448. I got to be honest with you though, and this is really what I'm going to say I don't like about this guy over here, that 448 is going to be a more difficult number to deal with, right? So I want to go through that with you, and I'm not suggesting you do this. I'm just suggesting it's a more difficult number. Now I got to be honest with you. In the end of it, I'm going to get this number over here. So what I'm going to claim over here, it's probably a good idea to look for a perfect square that's in 448. So I'm going to say 448. I'll write this down for you. Definitely contains a 4. 4 times what? 112. All right, 4 times 112. All right, now I'm going to look at the 112 and what does it contain a perfect square? Now someone says, I don't know what the perfect squares you're looking for. Well, I'm going to just simply discover them by taking the 112 now and factoring it. Now what a perfect square with 2? What would you get? 2 times what? Well, that gives you, let's see, 50, 55, 56, right? You get the idea, right? And I'm going to say 2 times, well, 2 times what would give you 56? 2 times, let's see, 28, right? Yeah, let me see if I made a mistake somewhere. That's why I like the 448. 448, did I do that right? Let's see, 7 times 24. I'm going to do that multiplication again. Again, I'm not saying I'm wrong, by the way. I'm just saying that I'm not seeing what I want. 24 is 27. Let's see, 2 times 24 is 480. Oh, there it is. That's 4. I made a mistake, and I apologize. I guess I'm sleeping. It's going to get all erased. I'm going to do it again. So 24 times 27. Mistakes happen. Let's see. I'm going to say 2 times 24 is 480. And 7 times 20 is 140. And 7 times 4 is 28. So if I add that together, let's see what you get. You get 8. Let's see, 14, 648. And again, I really can't say it's not. This is why I don't want you to do this. And we'll go through many more examples. So 648, let's write this down now. I'm going to say, let's see, 4 is a perfect square. 648. Let's see, 1, 4, 24. That's going to be 6. That's 24 and 8. And I get 2. So 4 times 162. Get my eraser out. And again, this is why we don't want you doing this. It just requires so much work. Let's see, 162. Well, I'm going to say I see 81 immediately. So 648, 4 times 81 times 2. So I can write this down as the square root of 4, the square root of 81, and the square root of 2. What's square root of 4? 2. What's square root of 81? 9. Square root of 2 is just the square root of 2. What does that give me? 18 root 2. Do we get the same number? Of course we do. All right. So I'm going to discourage that multiplication business. And you'll see as I'm doing problems over here that I'm basically going to do some simplifications if I can. Now, do I vary it? Sometimes I do vary it. All right, let's go to the next one, which is going to be dividing radicals. Oops. All right. So we have a quotient. And we can write this down instead. Now, by the way, I'm not going to say one is easier than the other, but I do want to look at an example. An example I want to look at is this one right over here. All right. So if I were looking at this one over here, what I would say over here is just looking at it. And if I were presented with this over here, oops, I keep doing that. I know that. If I saw the root of 125 over the root of 50, I mean, there's many things I could do. I could simplify this by looking at perfect squares. And I'm going to say, root 25. And there's many ways to do it. Don't think there's one way to do it. Root of 5. And this would be, well, the root of 25 times the root of 2. Well, the root of 25 is 5. So 5 root 5s over 5 root 2s. And what would I get over there? I would just get root 5 over root 2. And what could this be written as? Well, I could write this as a root of 5/2. And there's nothing wrong with that. All right. So I'm going to claim over here, I did it a slightly different way over here. What I do, I just did the ratio, 125 over 50, and did a reduction. Let me go through that with you. So if I looked at 125 over 50, and I would recommend doing this, by the way. I'm going to say, 25 goes into both, and that would be 5 over 2. And that's where that 5 over 2 is coming from. All right. And I got to be honest with you, though, there's a trouble here. And someone says, I don't understand why there's trouble. But this over here, whoops, I did it again. Is considered a no-no. I'll tell you why. The radicand, and this is the radicand, cannot be fractional. So I just rewrite it. I get root 5 over root 2. By the way, this is a no-no. And what's a no-no over here? Well, this radical can't be in the bottom. We need whole numbers. We can't have these things at the bottom. We'll make them whole. One way to do it is to multiply by a builder. And what are builders? Numerically, they're 1. Root 2 over root 2. We'll do it through many more examples. What's 5 times root 2? I'm sorry, what's root 5 times root 2? Root 10. What's root 2 times root 2? Root 4. What's root 4? 2. That's considered the proper answer. All right. We're going to go through conventions next. All right, let's go to that. All right. Conventions can be nasty, and we'll go through many examples. It can be a really tough section for a lot of students because not only is the lecture long, the examples tend to drone on for some time. To get the simplest radical form, your radical expression must meet these conditions. Let's talk about them. The radicand. Let's remind you what the radicand is. This thing here is the radicand. Okay, what does it say? The radicand contains no factors. That's a perfect power. What power are we talking about? We're talking about this power. So if it's a square root, we're looking for perfect squares. If it's a cube root, we're looking for perfect cubes. If it's a fourth root, we're looking for perfect fourth powers, so forth and so on. It goes on to say this certainly depends on the index, and it does. It depends. on the index of the Radicand. Depends on this. We'll certainly do examples and discuss it. All right, next two, pretty nasty. Let's talk about one step at a time. The radicand cannot be a fraction. So we have a simple rule for that. Nth root, well, let me go back to my pen, sorry. The nth root of a fraction can be written as the nth root of A over the nth root of B. Well, that's certainly taken care of. But then you got an additional problem. The additional problem is going to be this guy. A fraction, whoops. A fraction cannot contain a radical divisor. So this here is a no-no. And what we're going to do is try to rationalize it. We are going to go through examples though. As we go through examples, the problem with examples is there's going to be a large number of examples. These examples will start easy and move forward one step at a time. We'll do number one, then we'll do number two, then we'll do number three. Our goal is to be able to do simplest radical form and some basic arithmetic operations, addition, subtraction, multiplication, and division. All right, thank you.